Hello everyone, welcome to my Your Programming Club. Today we will be solving another daily lead code problem, and the problem's name is minimum bit flips to convert number. Okay, the problem statement goes like this: a bit flip of a number x is choosing a bit in binary representation of x and flipping it from, if it is 0 then it will be set to 1, and if it is 1 then it will be set to 0. Okay, so this is what a bit flip is. And for example, if the number is 7 and its binary representation is 111, okay, and you may choose to flip any bit including any leading zeros, okay, and flip it, okay, and we can flip the first bit from the right. Okay, so this was the first bit from the right, and if we want to flip it then it is 1 and it will be flipped to 0. So 1 to 0 and 0 to 1, and flip the second bit if you want, then this is the second bit from the right, so it will be 0 1 0 1. Okay, and if you want to flip the fifth bit, okay, the leading 0, so it will be this. So the first bit, second bit, okay, the third bit and the fourth bit, and this is the fifth bit that we have just flipped. Okay, so it was a leading 0, we can flip that one also. Okay, and given two integers start and goal, you have to return the minimum number of bit flips that will be needed to convert the given start number equal to the goal number. Okay, and before thinking of an approach, let's have a quick look at the at the constraints. Okay, so according to the constraints, the order of these inputs start and goal number will be of 10 raised to power 9. And so let's see how we can solve this particular problem. So what I can tell you is this 10 raised to power 9 can be very well fitted within the 32-bit integers. Okay, in 32-bit integers binary representation, the very leftmost bit is the most significant bit. It is for representing for the of the sign of the number, and rest of the bits from 0th bit to the 31st bit or 30th bit. Okay, uh, if it's we are taking first bit as the 0th bit, then it is they are used in the binary representation of the magnitude basically. Okay, and this is used for indicating the sign of that number. Okay, so 0 to 30th bit, in total you can say 31 bits. Okay, so 10 raised to power 9 can be very well fitted within this range. Okay, now going back to the problem statement. So let's see how we can solve this, and let's take a the first example for that, and let's try to understand how we'll be doing that. Okay, so in the first example, the start number was 7. Okay, so and your goal number was 10. Okay, binary representation of 7 is 1010. Okay, this is the binary representation of 7, and binary representation of 10 is 0111. Okay, so if we want to set make these numbers equal, then their binary representations must be equal. Okay, so the very first observation that you must make is that we somehow need to make their binary representations exactly identical. In that way, we would be able to achieve the identical numbers. Okay, so the very next thing that should be coming to your mind is, if we want to make the binary representations of both of these numbers equal, then we will be wanting to flip just only those bits which are different in both of them. Okay, so let me write it on a separate slide. Flip only those bits which are different in start and goal. Okay, so in order to find the different bits between start and goal, okay, or have a number representing or having set only the bits which are different in start and goal, we will be taking a XOR of both of them. So what does this XOR operation does is, whenever two bits are different, then only the corresponding bit in the result of the XOR operation will be set. Okay, if it is a 0 and 0 XOR, 0 bit and 0 bit XOR, then you will obviously get 0. If it is a 1 and 1, then also you will get 0. Okay, and if it is the other case, that if either it's a 1 or 0, then also 1, or if it is 0 or 1, then also it is 1. Okay, so this is the nature of XOR operation. So see, here the bits were different. Okay, let me change color here. So see, these bit positions were different. In one of those it was unset to or equal to 0, and in another number it was set or equal to 1. So XOR of those bit positions comes out to be set bit, okay, or 1. Okay, so this is what we are doing. See, and here those bits were same. Okay, both were set. So the XOR of those bit positions comes out to be 0. Okay, and similar will be the case for other things. Okay, so I hope till now you are able to understand. Then what we have to do is, we will be getting this different number. This number is having only those bits set which are different in both of the numbers which are start and goal. Okay, then you have to just return the number of bits set in different number. Okay, the second thing is, return the number of bits set in different number. This different number will be equal to the XOR operation of start and goal. Okay, so for counting the bits, we are using a kind of technique. I will also show you its implementation. So what we will be doing is, the very first thing, so this thing will continue till your different number is greater than 0. Okay, so this is the condition that we will be doing operations till the different number happens to be greater than 0. Okay, 0 is nothing but that all the bits are set to 0. Okay, so firstly you will subtract 1 from different number. Okay, and what does this subtracting of 1 does? So see, for example, if the binary representation of current binary representation of this particular different number is this, okay, and you want to subtract 1 from it, and one's binary representation will be this. Okay, so since we were dealing with only 4 set bits, so the most set bit was on the fourth position. That's why I took this kind of binary representation. Anyways, this is binary representation of 1, and if you subtract it from the number earlier, so this number, and if you want to do a subtraction of both of them, you will be getting something like this. Okay, so once you have this, then you will be wanting to do a AND operation of this particular number and the original number, which was this number. Okay. And in the AND operation, what happens is when both of the bits are set, only then the resultant the bit in the result will be set. So if we are doing AND of these two, then these two, one is unset and one is set, so 0. Both of them are unset, so 0. Both of them are set, so 1. Both of them are set, again 1. Okay, so this will be your result. Okay, so your different number is now updated to this particular number 110. Okay, so new different number will be generated. Then again doing the same operation, subtracting 1. See, subtracting 1 from this particular one will get you this. Okay, and then you will do the AND operation of this particular number which you got by subtracting 1 from the different number with the original different number. Okay, so see, in each operation what we are doing is, uh, let me write on the next slide. So we are turning off rightmost set bit. Okay, turning off rightmost set bit. So see, if the binary representation was this, on the very first operation this bit was gone and you were only left with this. Okay, now this is the rightmost set bit. On the second operation this particular will be gone and you will only be left with this particular one. Okay, and on the last operation the only remaining bit will be gone or turned off and you will be left with only zeros, and then you will stop your operation basically. And that is essentially what is happening inside this particular series of operations. Okay, so then again you will get your new value and again subtracting 1 from it and then again doing a AND operation, and which will result into 0 and we will eventually stop. So how many number of times this uh, operation series or number of these operations were repeated? So it was repeated 3 times. Operation count is 3 times, so that's why 3 set bits. Okay, essentially we are turning off the rightmost set bit. So how many times you turn flip you know press the switch is equal to the number of set bits. Okay, so this is what you have to return. Now let's quickly see the implementation and let's take a fresh slide for that. So this is the implementation. So see, as we discussed that we will be needing the different number which will be having set bit which are different in both of the numbers, and both of the numbers are start and the goal. And let's change color here. Okay, start and goal. So the different number will be found, will be we will be finding that by doing XOR operation. Okay, and because of the nature of XOR operation, only when the bits are different it will set into it will set our that corresponding bit position. Okay, so once you are having the different number, then it's just that you have to return the number of set bits in the different number. Okay, so set bit count, and this is the function that will implement that functionality. So initially you will be having a bit count. It is the number of times you do the following operation. Okay, and you will do the following operation till when your number is greater than 0. So or another way of saying it can be that all the bits in that number are turned off. Okay, so we are turning off the rightmost set bit by doing this particular operation. Okay, and then we are just returning the bit count. Okay, so now let's have a quick discussion about the complexities also. So time complexity wise, see, since the number of bits I already told you that only 31 bits will be needed, because of the nature of the constraints, that it is either 0 or it can go at max up to 10 raised to power 9. Okay, so order of 31 you can say. Okay, and if you want to take it as a constant, then it will be order of 1. Okay, anyways, this will be the time complexity. And space complexity wise, you must have guessed that since we are not using any extra space here, uh, just using one variable and then some variables in the function below, then we can say that it is order of 1, or constant you can say. So these are the complexities, and this is the approach. If you are still having any doubts or any queries in general, then please feel free to ask them in the comment section. And I really hope this solution walkthrough added some value to your journey of honing your DSA skills. Keep solving more and more problems, and I will be seeing you in the next video. Thank you for watching.